Nah, okay.
Okay, good afternoon, everybody. We will continue the same class in the previous one. Okay, we are discussing about how to estimate the diffusivity coefficient, DAB. Okay, there are two methods to estimate the diffusivity coefficient, DAB. So, first one among those is twin bulb method. I will put off my video. Okay, yeah. The first one among those methods are twin bulb method. In the twin bulb method, what will happen? The gas A and gas B is filled in their respective bulbs, bulb A and bulb B. And these both bulbs are separated using some valve or some porous plug. Okay, after some when time t is equal to 0, the plug will be removed. The, uh, the barrier, this barrier will be removed. And after that, what will happen? The gas A and gas B will be filled in their respective bulbs, bulb A and bulb B. And the gas B will be filled in their respective bulbs. particular depending on their affinity towards each other, they will just diffuse in each bulb. After some time, say for example 1 minute, after 1 minute the bulb will be, once again the wall will be closed, and the concentration of gas A will be checked in this bulb, and concentration of gas B will be checked in that both bulbs. Then see, in a similar fashion at regular intervals of time, when t is equal to 1 minute, t is equal to 2 minutes, t is equal to 3 minutes, like that way the compositions will be analyzed. Then we will clearly know that how much the composition, how much the change in composition has been observed in each bulb and in each gas concentration. Depending on the flux formulas, we can evaluate what is DAB. Okay. And other method for the liquid diffusivity calculation is, some volatile liquid will be filled here in a test tube, and the top of this test tube air is just blown. So air we are indicating as B. So A is this volatile liquid. Whenever the gas is passing from the top of this test tube, the gas will carry some of the particles of volatile liquid A. So A plus B will be coming out. Already the composition of gas which we are passing, whether it may be air or some other gas which we are passing, already known at the initial conditions, already known. Then the concentration or the height of this liquid, we already know what is the height of the liquid. Whatever the differential height which has been transferred into the surrounding liquid is nothing but a diffusion path, change in that liquid height. Then the composition here will be analyzed. Depending on the formulas, same diffusivity DAB will be calculated. Okay, these two methods are available. You can see during our laboratory experiments, this experiment is there for us. Stefan tube method is there. Okay, for our laboratory, this twin bulb method is not available. So you can see in detail. Okay, then what about in the absence of some experimental data for the gases, for the precious gases or for the precious liquid, whatever the gases or liquids are there, they are very much precious. For that one, what we have to do? We have to do, if there is no experimental data, we can't find through experiments TAB value. Then what we have to do? We have to apply certain correlations. Correlations are nothing but the experimental facts. Okay, many scientists have conducted the experiment for many gases and liquids, and they observed a similar phenomena. Okay, depending on their physical properties, depending on their whatever the operating conditions, some of the rare phenomena they have observed. Those finding that facts through the experiments, and they have formulated one correlations that are nothing but a experimental facts. So now the first equation is the Wilkie equation. Okay, this equation is applicable for gases, only for the gases which are non-polar. Okay, already if there are some polar gases, polar substances are present in non-polar gases also, then this equation is applicable. This is called Wilkie-Lee equation, or simply we can call Wilkie equation. So DAB is equal to 10 power minus 4 minus 0.249 root of 1 by MB plus 1 by MA into T power 3 by 2 into root of 1 by MA plus 1 by MB divided by PT, total pressure, gamma AB square, function of KT by epsilon AB. So what are these variables? We already know MA and MB are the respective molecular weights of a component A and molecular weights of a solvent, or some other component B. Then C, this is temperature, absolute temperature, power 3 by 2. Then same molecular weights, then PT already know pressure, to it's a total pressure. Then gamma AB is nothing but molecular separation factor. Okay, molecular separation factor at collision. What will happen? The molecular level, it will show that properties here, gamma AB square. So this is function of KT by epsilon AB. In this K is Stefan-Boltzmann constant. This is called Stefan-Boltzmann constant. Then T is absolute temperature. Epsilon AB. Um, epsilon AB is nothing but a collision factor. Okay, this collision factor can be estimated using this formula. Epsilon by T is equal to 1.21 TB. TB is nothing but normal boiling temperature. When when the two gases are there in the mixture, we can use this formula. Epsilon is equal to root of epsilon A into epsilon B. The function of KT by epsilon divided by T we can find out. So from this epsilon divided by T, we can reverse reciprocal of this equation is nothing but this one multiplied by Stefan-Boltzmann constant is then we can obtain function of KT by epsilon B. Okay, in the problems, many problems has been asked to solve for DAB, this equation to solve for DAB. You can go through that problems. We will discuss that problems also. So next one is the liquids equation. This is equation which is called a Wilkie-Chang equation. Okay, this equation is applicable for liquids. Okay, then what is this equation? DAB is equal to 117.3 into 10 power minus 18. This is psi MB, psi into MB power 0.5 T divided by mu into nu A power 0.6. Then what is psi? Psi is nothing but an association factor for solvent. This signifies what is the association of that particular solute to that solvent. Okay, this is the association factor for solvent. MB is the molecular weight of the solvent, power 0.5. Then T is the absolute temperature. Nu is the viscosity of the solution. Then UA is nothing but a molar volume of solute. So what are these properties? So association factors we can directly uh, have a value. If this association factor, if the solvent used is a water, then this association factor value is 2.26. If this solvent used is methanol or methanol, then we can say this psi value, then directly we can substitute 1.9. If this is the solvent, solvent is ethanol, then this is psi is equal to 1.5. If this solvent is a benzene, then it is 1.0. So MB is obviously molecular weight of solvent. If that is benzene, then we have to substitute the molecular form. And T is the absolute temperature, mu is viscosity. It will be given in the problem, and mu A is the molar volume of solute. Okay, we have to estimate that one, or whether it may be directly given. Okay, the value of 0.756 is only applicable where solute water is acts as a solute. Then A is also solute. Then only this 0.756 will be applicable there. The next one we have already discussed about is mass transfer coefficients. Okay, mass transfer coefficients is nothing but a diffusion rate constants. Okay, that are related that relates the mass transfer rate, mass transfer area, concentration change as driving force. Okay, then mass transfer coefficient is defined as the ratio of flux to driving force. Okay, this is defined as mass transfer coefficient is defined as the ratio of flux to driving force, and it is usually expressed in the units of moles transferred. Okay, moles per unit time is molar rate, rate per unit area into driving force. If the driving force is pressure, it will be a pressure gradient. If the driving force is concentration, it will be a concentration gradient. If the driving, then this is XA. Okay, so it is defined in such a fashion. Then how, what is the use of this mass transfer coefficient? Okay, whenever we estimate the mass transfer coefficient, whenever our mass transfer operation is associated with more than one phase, it is very convenient. Okay, it is very convenient to conveniently express what is the diffusion rate of a particular solute in this particular solvent. Otherwise, for any immiscible and partially miscible fluids, can also we can find this mass transfer coefficient. These mass transfer coefficients are largely estimated for the design principles. Okay, for the design convenience of the separation equipment, these mass transfer coefficients are very much required. Okay, whenever there is some spillage, okay, whenever there is some gas leakage, some toxic gas is leaked around the surrounding environment, then how much life that surrounding gas, that leaked gas possesses in that surrounding environment, we can estimate through the mass transfer coefficient. Okay, we can say what is the impact of that particular gas and how many days or how many years or how many months it is going to impact the surrounding environment. We can estimate, we can say by using the mass transfer coefficient. These are the advantages of mass transfer coefficient. Then mass transfer coefficients are defined as a flux is directly proportional to, we already know this from the Fick's first law of diffusion. Flux is directly proportional to any type of gradient, whether it will be concentration gradient or a pressure gradient. Simply we can refer to as a driving force. Okay, now the proportionality constant here is nothing but a mass transfer coefficient. So whatever the flux is there, apart from flux and driving force, whatever the quantities are there in the equations, so all that quantities are clubbed into a single quantity called mass transfer coefficient. So flux can be expressed in the Na or J, we can say Na here. See, it is proportional to concentration gradient. See, Ca1 minus Ca2. Then this proportionality constant is, because this driving force is C, it is indicated as C. So mass transfer coefficient we can denote as C. Because it is in liquid phase, so we can denote as KL, KC or KL. Similarly, when the driving force is expressed in mole fractions, then we can indicate our mass transfer coefficient with the subscript as Kx. Okay, when we indicate our driving force as pressures, then we can indicate our mass transfer coefficient as Kp, or this is because of gas phase. So Kg we can denote Kp or Kg here. At the same time here, when we express our driving force in terms of gas phase mole fraction, then we can denote it mass transfer coefficient as Ky. So therefore Kc, Kl, Kx, Kp, Kg, Ky, all these are nothing but mass transfer coefficient. Whatever the flux formula is there, apart from this flux denotion Na and this driving force, whatever the quantities left in between them, in between these two, are known as a mass transfer. These are the equations which we already derived previously in the A through non-diffusing B case for the liquids, for the gases, and equimolar counter diffusion case for the liquids and gases. Okay, I have written separately here. Just see, according to mass transfer coefficient is nothing but flux is directly proportional to this gradient. Okay, apart from this flux and gradient, whatever the quantities left is nothing but a mass transfer coefficient. Okay, this is called, because this driving force is expressed as C concentrations, so we take this mass transfer coefficient with this whole term as a mass transfer coefficient Kc or Kn. So this indicates liquid phase. This indicates the concentration driving force. Then the next formula is when we express our driving force in terms of mole fractions, then we can indicate this as a mass transfer coefficient Kx. So this is whole quantity is nothing but a Kx. Okay, that's separate. I have written here Kx is this one and Kl or Kc is this one. So similarly, for the liquids case, in the case of equimolar counter diffusion, the same formula we can observe. Apart from flux and driving force, whatever the quantities left is nothing but a mass transfer coefficient. So this is expressed in C quantities. This here it will be C. But in order to differentiate between these two cases, A through non-diffusing B and equimolar counter diffusion, we are just putting the dash in case of equimolar counter diffusion, whereas this is simply Kc in case of A through non-diffusing B. So similarly Kl or Kc. And here also this is the equation which is applicable when the driving force is expressed in mole fractions. Since this is the mole fraction, we can denote this as a mass transfer coefficient expressed in a mole fraction. Kx dash will be there. So this is the Kx dash. When this C is expressed for liquids, rho by m average, this is also called as a Kx dash. So separately I have expressed written this equation here. So to convert these from one form to another form, Kx to Kl form, or Kl to Kl dash to Kl form, and Kl to Kx form, this is the standard formula we can use. Okay, we can cancel out the whatever the common terms are there, and we can see. For example, see Kx dash. Okay, Kx dash is equal to Kl dash into rho by m average. So Kl dash is nothing but dAb by z, whereas Kh dash is only dAb by z into rho m. So multiplying this Kl dash with rho by m, it will be equal to Kx dash. That's the meaning of this formula. We can estimate the different one when one mass transfer coefficient is estimated at one condition, at one driving for using one driving force, the another mass transfer coefficient can be easily estimated using this formula. And similarly for the gas phase mass transfer coefficient, same for the both cases, A through non-diffusing B and equimolar counter diffusion, same derivations we have conducted and derived these equations. So from the first flux definition, from the mass transfer coefficient definition, flux is directly proportional to this gradient or a driving force. Apart from this flux and driving force, whatever the quantities left in between is nothing but a mass transfer coefficient. So this is expressed in P. So this is Kp. This overall mass transfer coefficient is Kp. Because this is a gas phase, we can also denote this as a kg. So kp or kg is nothing but dABpt by RTZ into PBLN. Okay, then this is applicable when the driving force is expressed in terms of mole fraction, gas phase mole fraction. Apart from whatever the flux and driving force, whatever the quantity left is nothing but a mass transfer coefficient. So our driving force is expressed in y quantity or the mole fraction quantity. This is a mass transfer coefficient ky. So this is a ky. dABpt by RTZ YBLN is nothing but ky. Similarly, for the case of equimolar counter diffusion, since this is expressed in P, driving force is expressed in P, so this is Kp. Since this is equimolar counter diffusion case, we have to put Kp dash or Kg dash. Okay, same formula I have expressed here. Similarly, here also, when the driving force is expressed in mole fractions, Y, this is Ky. Because of this is equimolar counter diffusion case, we can express this as Ky dash. That's the same formula. Okay, this is the conversion formula, overall conversion formula. We can convert from Kg dash to Kg, and this Kg to Ky, this Ky to Ky dash. We can convert this using this standard formula. Okay, these are the overall mass transfer coefficients. Okay, in the examination point of view, they can ask any one case A through non-diffusing B for the gas cases. derive what derive the what is the mass transfer coefficient, they can ask in such a way. Okay, then you have to derive one case A through non-diffusing B case, then you can write whatever the quantities left apart from flux and driving force is known as a mass transfer coefficient. You have to write this formula along with that derivation, complete derivation. Okay, then the next topic is the theories of mass transfer. Okay, we already said that there are many theories for the mass transfer. Okay, to explain what is the phenomena is taking place in between different layers. Okay, so these theories are nothing but first one is the film theory. This is the oldest theory, film theory. So what this film theory is saying, according to Whitman, this is proposed by Whitman film theory. This is known as Whitman film theory. Whitman, he is saying whatever the mass transfer is taking place, only through the film mass transfer will take place. Okay, a thin film will be formed around the mass transfer surface. Then whatever the mass transfer is taking place, it will take place within this thin film, he is saying. Okay, there are certain assumptions like steady state, etc. So we'll discuss this one. Then penetration theory. Then penetration theory, this film theory is applicable for steady state only. Okay, whereas film theory has a drawback like it is applicable for steady state, and at the same time it doesn't give any estimation mechanism of delta. Delta is nothing but film thickness. Whereas in penetration theory, they are suggesting that theory for the unsteady state condition. Usually, the mass transfer operations are applicable for unsteady state conditions. So many operations in the industrial scale, almost every operation will be a unsteady state, means which is dependent on time, which doesn't have a independence of time. So film theory has a rare application in the real cases, whereas surface renewal theory, penetration theory are the unsteady state theories. So these theories are applicable for the real industrial scale problems with certain exemptions. Okay, surface renewal theory. So penetration theory is saying around some bubble, some liquid particles are forming some packets. Same theory he is also proposing with certain modification. That packets, whatever the packets of liquids are forming, will have a equal residence time. Whereas in the surface renewal theory, each packet will have a different residence time. He was suggesting. Okay, we will discuss this one. And two film theory. This is the extension for this film theory. Okay, when only one phase is there, then film theory is applicable. When more than one phase is there, then two film theory will be applicable. See here, there are two films. Liquid boundary will be there, liquid film will be there, and gas film will be there. For this, we have to go for two resistance or two film theory only. Okay, now film theory. Film theory was proposed by Whitman. It is the oldest theory. Okay, it is applicable for one-dimensional convective mass transfer. So you can see the what he is saying. Whatever the mass transfer takes place will takes place within the film. The film will be formed immediately on thin film only the mass transfer takes place. When we verify the concentration profile, the initial concentration of A is Ca naught. Then it will go a transformation up to the bulk concentration. Okay, after the film thickness crosses the film thickness, the mass transfer concentration will be same as that of bulk. Okay, when the concentration profile we see in the stagnant film region, this is the concentration profile. Okay, whereas the film thickness is varying, then the concentration profile will be look like this one. Okay, real in the real terminology, the concentration profile will be like this one. In the ideal terminology, we can consider a straight line. Okay, straight line as this actual concentration profile in stagnant region. So this film will have a thickness of delta. So assumptions here is this is applicable for steady state theory. This is a steady state theory, and at the same time, whatever the mass transfer is taking place only through the film. Okay, and the mass flux is zero, and the mass transfer occurs at very low concentrations. Okay, very low concentration changes will only occur because the film will have a very thin film. It is a very thin film. So the when we solve our equations, okay, when we solve our relationship between diffusivities, we will get Na is equal to Ja because N is equal to 0. In that case, Na is equal to Ja. Then we can substitute Na is equal to Ja. In place of Ja, we can substitute Fick's first law of diffusion, which is minus dAB dou Ca by dou Z. After integrating the Fick's first law of diffusion, we will observe this equation. Na is equal to dAB mass transfer. Here the film here the mass transfer surface is nothing but this only this film thickness. Inside this film only the mass transfer is taking place. So our path of mass transfer is only this delta. So in place of Z we are substituting delta. So 0 to delta, limits for Z will be 0 to delta, limits for concentration dou Ca will be Ca naught to Cab. So these are the limits. So when we solve this equation, we can observe this. So from this equation, the definition of mass transfer coefficient, apart whatever the quantity is left apart from flux and concentration difference, is called a mass transfer coefficient. So here in this case, dAB by delta is KL. This is a liquid phase mass transfer coefficient. So from the film theory, what it is saying, the flux is directly proportional to the diffusivity. See here from this equation, this is applicable only for the laminar flow, he is saying. Then in the turbulent flow, what is the equation applicable? This equation is applicable. Flux is also directly proportional to diffusivity, but to the nth power in the turbulent flow. So this n is dependent on the operating conditions of that particular equipment. It can take a quantity, it can take a value in between 0 to 0.9. The film theory is saying that flux is directly proportional to the diffusivity. This is applicable for laminar flow, whereas flux is directly proportional to the diffusivity power n. This is applicable for the turbulent flow. This n n will take a value in between 0 to 0.9 depending on the operating conditions. So this film theory will have a drawbacks. So the first drawback is he doesn't give a clear cut understanding that how to estimate this film thickness delta quantity, how to estimate this delta. He doesn't give what is that one, how to estimate this one. So next one is this film theory is applicable only for the steady state. Okay, this is not applicable for the unsteady state conditions. Okay, steady state. So many industrial operations, almost all the industrial operations will take place in the unsteady state conditions. So this film theory cannot be applied for the unsteady state conditions. So Higby proposed the penetration theory. Okay, this penetration theory yeah, has the assumptions that this is applicable for the unsteady state conditions. Then there is an equilibrium exists between this liquid and gas, and each liquid film, each the liquid packet will stay for the equal period of time, same period of time. These packets will stay. What he is saying in the absorption column, for example, if you consider this as absorption column, the gas is flowing counter currently to the liquid. Liquid is entering from the top and gas is flowing from the bottom. Then liquid is just dropping like this one. So gas is just entering into the liquid. Then whatever the gas is entering into the liquid and it is rising. Throughout this rising of the bubble, these liquid particles will form as a packet around the circumference of this sphere or nothing but a bubble. Okay, around this circle. Then the packets will move around this circle towards the down. Okay, whatever the mass is exchanging in between them will exchange throughout this circle path. then it will be dropped out. The bubble will just rise and uh, go outside of this column. So he is saying this liquid packets will stay for equal period of time. Okay, this for example, this is packet 1, this is packet 2, this is packet 3, this is packet 4, this is packet 5, this is packet 6. All the 6 packets will stay for the same period of time. For example, packet 1 is staying for 1 second, so this all these remaining 5 packets will stay for only 1 second only. Okay, then these are the assumptions for the penetration theory. This was proposed by the author Higby. Okay, then fixed second of diffusion will be applicable because this is an unsteady state condition. For the unsteady state condition, fixed second law is applicable. This is the equation. Because this is sphere, in place of z we are substituting radial coordinate. Okay, radial coordinate. Okay, then this is in place of dou square ca by dou x square or dou y square or dou z square, we are substituting r square. So dou ca by dou t. This is unsteady state variable. After solving this equation through some error functions, then the solution will be this one. Okay, you have to write in the examination point of view, they will ask write about any two theories of mass transfer, or write about the penetration theory of mass transfer, or write about the film theory of mass transfer, or write about the surface renewal theory of the mass transfer. So when they are asked, you have to write about these equations and all the assumptions and explain the phenomena. This is the phenomena taking place, this is the bubble through which it is rising, the liquids will form a packets. We have to explain in our words, then we have to write this equation. Since this is unsteady state assumption, we have to write the fixed second law of diffusion, then the solution will be this one. So you don't have to go for clear solution. If you are interested in obtaining this solution, knowing about this solution, you can ask me anytime, but before that you have to refer what are the error functions. Okay, the after this solution, the applicable equation will be this one. Okay, after solution we can obtain this one. So from this we can say flux is not directly proportional to square root of dab, whereas in film theory flux is proportional to dab, directly linearly proportional. Here flux is proportional to the square root of dab, so dab power 1 by 2 here. So next one is the surface renewal theory. The author Dankworth proposed this surface renewal theory. He just modified the penetration theory. Just he modified the same theory, penetration theory, into the surface renewal theory. What he is saying, the same phenomena will be observed, but these packets will have a different period of time. Will stay for the different period in around the bubble. For example, this packet one will stay for 1 second. Say for 1 second, this packet will stay for another 1 second or 2 seconds, 3 seconds. Okay, whatever its convenient time, it will stay around this bubble. Okay, need not be same. Packet 1 is staying for 1 second, and packet 2, packet 3, packet 3, packet 4, packet 5, packet 6. This doesn't have to stay for equal period of time, same period of time. Okay, this doesn't have to stay for same period of time, whereas this penetration theory, these packets needs to be stayed for the same period of time, whereas this surface renewal theory, these packets will have a different time, different period, they will stay around this bubble. Okay, this was the surface renewal theory. This is also applicable for the unsteady state theory. Okay, the liquid elements at the interface are being randomly swapped by fresh elements. Okay, whenever they are replaced, these fresh packets are replaced, this already consumed packets are just dropped at the bottom. The fresh packets will come and attach to this bubble, he is saying. This is the second assumption. Then at any moment, each liquid element at the surface has the same probability of being subsidized by a fresh element. That's what. If the packet 1 is just dropped out, okay, the packet 1 is just dropped out, then this packet 1 is immediately replaced by another, some fresh packet. Okay, that's what he is saying. So he has directly given this equation. There is no derivation for this also. He has directly given this equation. In this also, flux is directly proportional to the square root of this DAB, diffuse. Okay, yeah, for example, this is a new packet of solvent. Okay, this is already consumed packet or a saturated packet of solvent. Whenever from the surface this packet has dropped, immediately this packet will replace that one. Immediately this packet will attach to this one. That's what he is saying. This is the fraction of surface. Fraction of this surface is renewed in unit time, in unit second. Okay, so that is called in second inverse. So this S will have a second inverse units. So this is about the surface renewable theory. Then the two film theory. Okay, I have shown you one video also regarding this one. NH3 plus air is just diffusing into the water, in which NH3 is solubilizing in the water, whereas air is not at all soluble. That is also a case for the example case for the A through non-diffusing B. So in that one, there are two film resistances. One is the gas film resistance and liquid film resistance. Bulk phase to the gas film, and then from gas film onwards the mass transfer will takes place throughout this film, and after that liquid film resistance will be observed. Through the liquid film, the resistance liquid film resistance, the concentration change will takes place like this one. After the liquid film, the concentration will be same as that of bulk liquid phase. Okay, before this before this film gas film, the same concentration of bulk gas concentration will be same. So these are the equilibrium concentration. C star and P star are nothing but equilibrium concentration and equilibrium partial pressures. Okay, from the definition of mass transfer coefficients, we are assuming when we are writing the overall balance, we have to write PA to PA star. This we have to use the overall gas phase mass transfer coefficient. When we are writing for the concentration CA star to CA, we have to use the overall mass transfer coefficient for the liquid phase. When we are writing for the single phase, for say for the gas phase, we have to use individual mass transfer coefficient. For example, PA to PAI, the pressures are changing. So PA to PAI, we have to use only individual mass transfer coefficient Kg. Okay, whereas when we are using the concentration profiles from PA to PA star, we are using overall mass transfer coefficient Kg, KOG or KOL. Okay, these are the case using these two individual mass transfer coefficient. The relationship between this individual mass transfer coefficient and overall mass transfer coefficient can be found out. Okay, you can watch these previous videos how we have solved these equations. Then there are some special cases. There are two special cases in which these equations can be simplified. The first one among is highly soluble gas. When there is a highly soluble gas like NH3 is highly soluble in water, for that case, we need not to go to estimate the mass transfer coefficient in liquid phase. We can directly correlate that because that gas is highly soluble in liquid. So estimation of only individual gases mass transfer coefficient is enough. That is enough to find out overall mass transfer coefficient. We need not to go for this estimation of this individual liquid phase mass transfer coefficient. Directly we can cancel out this term for the highly soluble cases. Okay, then 1 by KOG is equal to 1 by kg. When gas is sparingly soluble, meaning when gas is very low soluble in the liquid, then we need not to go to estimate the gas phase mass transfer coefficient. Okay, we just calculate the individual liquid phase mass transfer coefficient, and we can cancel out this term. This overall mass transfer coefficient is equal to individual mass transfer coefficient in terms of liquid phase. Okay, this is this example for this one is oxygen. Oxygen is very low soluble in water. Okay, whereas NH3 is highly soluble in water. In this case, the example is NH3 is highly soluble in water. Because of that, we can estimate only gas phase mass transfer coefficient. In this case, oxygen is very low soluble in water. We can estimate only liquid phase mass transfer coefficient. Okay, these two are the special cases. In between cases, we have to estimate the both coefficient, both mass transfer coefficient in liquid phase and gas phase. Then we have to apply this whole formula. Then the last topic in this chapter, in this unit, is estimation of mass transfer coefficient using wetted wall tower. That Kc, Kg, Kp, Kl, Kx dash, Kl dash, Kc dash, Kp dash, Kp, etc. Everything can be estimated using one tower called wetted wall tower. Okay, the correlation used in estimation of this mass transfer coefficient is this one. When the mass transfer through the pipe walls, mass transfer is taking place through the one pipe called as tubular pipe. That case is also in a turbulent flow. Then this equation, this correlation can be used, in which SH is the Sherwood number. Sherwood number is given as KD by DAB, where K is the mass transfer coefficient, D is the diameter of the pipe, DAB is the diffusivity of A through B. Okay, diffusivity coefficient. Sherwood number is equal to 0.023. NRE is Reynolds number power 0.8, Smith number power 1 by 3, and this is viscosity correction factor mu by nu W power 0.14, where this mu is viscosity of the solution, whereas viscosity of the gas or liquid, whereas this nu W is the viscosity of a particular mass transfer equipment valve. Okay, SC is the Smith number. Smith number is given as the mu by rho DAB. Mu is the viscosity, rho is the density, DAB is the diffusivity coefficient. Okay, NRE is the Reynolds number. You might be aware of the Reynolds number from the fluid mechanics course. Reynolds number is equal to dV bar rho by nu, where d is the diameter of the tube, v bar is the velocity of the fluid, and rho is the density of the fluid, and nu is the density of the fluid. Okay, then this is the viscosity correction factor nu by nu W power 0.4. The similar equation you can see during the convection heat transfer coefficient. Okay, in that one Smith number, Sherwood number is replaced with Nusselt number, and Smith number you can find out in place of Smith number Prandtl number, NPR, Cp nu by K. You can see this one. Okay, similar equation you might encounter in the heat transfer course, in the convection heat transfer. Okay, this is the wetted wall tower, nothing but a absorption column in which same gas will flow counter current to the liquid. Okay, gas will enter from the bottom of the column and liquid will enter from the top of the column. Then gas will release from the top of the column and liquid will be released from the bottom of the column. This is the notation schemes. G is the gas flow rate. Okay, whether it may be when it is a mass, it is kg per second. When it is a mole, it is a mole per second. Okay, L, G, L, everything are same. It is whether it may be a molar rate or mass rate. When it is a mass rate, its units are kg per second. When it is a molar rate, it is a mole per second. Then these are the concentrations: Ca1, Ca2, Ca1 star, Ca2 star, Ca1, Ca2 star, and Ca1 star are nothing but a equilibrium concentrations. Okay, whereas Ca2 and Ca1 are the true concentrations. Okay, that particular concentration in the liquid phase. Pa1, Pa2, these are the partial pressures of a component A and at position 1 and position 2. After applying the mole balance or the component balance around this tower, we can obtain this equation: G into Ya2 minus Ya1 is equal to L into Xa2 minus Xa1. Then according to the mass transfer coefficient definition, flux is directly proportional to the driving force. In this, proportionality constant is mass transfer coefficient. So this MTC is mass transfer coefficient. Na is equal to mass transfer coefficient into driving force. Since this is a counter current operation, so for the counter current operation, the logarithmic mean driving force will be very much useful. Similarly, in the counter current heat exchangers, you might have encountered the delta T LMTD, which is logarithmic mean temperature difference. Similarly, here also for the counter current, since this is a counter current operation, we have to use the logarithmic mean pressure gradient or logarithmic mean mole fraction gradients. So delta PLN is the logarithmic mean pressure gradient, delta YLN is the logarithmic mean mole fraction gradient. So what is this delta PLN? Delta PLN is nothing but delta P1 at position 1, the difference between the pressures, as position 2, the difference between the pressure, divided by ln of this change in pressures. So what is delta P1? Delta P1 is, this is position 1. At position 1, the difference between PA1 and this PA star is nothing but delta P1 and delta P2. This is for the position 2. Here you see this is position 2. The difference between this one PA2 and minus PA1. Okay, this is called delta P2. Same divided by ln. Similarly, for the case of delta YLN, delta Y1 is, this is for position 1. So Ya1 minus Ya1 star is nothing but delta Y1. Then delta Y2 is for the position 2. This is for position 2. So Ya2 minus Ya2 star is nothing but delta Y2. So to convert the pressures to concentration or concentrations to pressure, we have to use the Henry's law. Henry's law is nothing but partial pressure is equal to Henry's law constant into concentration. P is proportional to C. Okay, in which the proportionality constant is Henry's law constant, where H is the Henry's law constant. Pa1 star is the equilibrium partial pressure. Ca1 is the concentration of component A at position 1. Ca2 is the concentration of component A at position 2. Pa2 is the equilibrium partial pressure of component A at position 2. So this one. So using these formulas, we can estimate the mass transfer coefficients. So this is the revision of unit 1. If you have any doubts, you can ask me. So if you know how to solve all these equations and everything, it will be very easy. If you are having any doubt, just watch the previous videos. Today's video also I just uploaded to the streams, Microsoft streams. Using that same link, you have to go through and see whatever the previous videos, previous classes, everything you can watch. Okay, I think old question papers. I think you received that old question papers, I guess. Have you received that old question papers, MTO?
Yes, sir.
Yeah, please go through that one. MTO, everything is just given in the notes, and same time problems also same from the from your old question papers only. Okay, we will try to solve one or two problems. Let's see what we have to do. Okay, these are the basic problems. Okay, how to estimate the mass density, how to mass concentration or the molar concentration. This is the first problem. Okay, this has been not asked in your old question papers, but because of to brush up your basics, I just given this problem. So here it is asking calculate the mass concentration of 2 grams moles of sulfur dioxide to be used to manufacture sulfuric acid in a zero point 0.2 meter cube of reactor. So what they are saying is 2 gram moles of sulfur trioxide is used, okay, is used in the manufacture of sulfuric acid. So in the sulfuric acid manufacture, he is saying to estimate what is the mass concentration. Mass concentration units are gram per cc or gram per meter cube or gram per liter. We have to estimate according to our convenient unit. So 2 gram moles of SO2 is there. Okay, 2 gram moles of SO2 is there. So SO2 molecular weight of SO2 we have to estimate first. This is SO2 molecular weight. So after estimating this, we will obtain 64 as a molecular weight. For the H2SO4 also, we have to estimate what is the molecular weight. We know 98, this is the molecular weight of H2SO4. Now, what is moles? Moles are nothing but weight by molecular weight, where MW is the molecular weight here. So we have to estimate weight first. Weight is equal to moles into molecular weight. Then 2 moles they have given gram moles, 2 into molecular weight. So gram moles will be cancelled. Left out will be only grams. 2 into 64. So W is equal to 2 into 64 divided by whatever the volume they have given. The reactor volume is 0.2. So this will come around 640 gram per meter cube. You can convert it to gram per liter. 1 liter is equal to 10 power minus 3 meter cube. Okay, using that formula, we can convert these to gram per liters. Okay, so in that way, you can estimate this mass concentration. Or when they ask about the molar concentration, what we have to do? C is equal to moles by volume. So N by V. So we can write N. N is already they have given 2 by 0.2 is nothing but molar concentration. C is equal to 2 by 0.2 is equal to some value it will come. So they have given the mass concentration. So rho is equal to 2 into 64. We have to use molecular weight extra apart from the only moles. This maybe probably you have seen in the material energy balance or the CPP course. So this is also a practice problem. A mixture of noble gases. Okay, whatever the noble gases are there, they have given helium, argon, krypton, and xenon. These are the gases mixture. In the mixture, they are present. Is at a total pressure of 100 kilopascal and a temperature of 200 Kelvin. So this is the total pressure. PT is equal to 100 kilopascal and fractions. Okay, equal mole fractions of each of the gases. So this means if a mixture has equal mole fraction of these gases means they are having an equal mole fraction. When we consider our basis as 1 kilomole, then this will have 0.25 kilomole, this has 0.25 kilomole, this has 0.25, this is 0.25, whole clubbed up to our basics as 1 kilomole. If you consider 100 kilomole as our basis, then it will have 25 kilomole. This is 25, this is 25, this is 25. All together we can say this is 100 kilomole mixture. So depending on the basis, we can solve this problem. So this statement is very important. If a mixture has equal kilomole fraction of each of the gases, meaning 25, 25, 25, 25, or 0.25, 0.25, 0.25, 0.25, then we can club it to the mixture assumption. So estimate or determine the composition of the mixture in terms of mass fractions. Okay, we have to determine the composition of a mixture in terms of mass fractions. Mass fractions is nothing but individual mass divided by total mass. So next one is the total molar concentration. So C we have to estimate. Here, since these are gas, Y we have to estimate. Y mole fractions. This is gases. So Y we have to estimate. Here the molar concentration. C we have to estimate. Then mass density. Mass density is denoted by rho, or the mass concentration we can say. So this is C, this is rho, this is Y we have to estimate. So assumption, we can apply the assumption. This is whole gas mixture is 1 kilomole, or otherwise we can take our basis as 100 kilomole of the mixture. When we take 100 kilomole, each composition will be of 25, 25, 25, 25 kilomole. When we take the basis as 1 kilomole, this will be 0.25, 0.25, 0.25 kilomoles. And we have to estimate the moles of each component of the mixture. So each component will have a, since we are taking the basis as 100 kilomole, each component will have a 25 kilomole as the composition. So from this composition we can estimate the total mass of the mixture. So total mass is nothing but mass mole fraction into whatever that molecular weight will be there, same we have to multiply. Sigma average molecular weight is nothing but sigma xi into mi. Same similar fashion we have to estimate the total mass of the mixture. The mole fractions of these noble gases are given here. See, for the helium 4 is the molecular weight, and for argon 40 will be molecular weight, 83.8 for the krypton, and xenon 131.3. So this moles into molecular weight will be weight mole, since moles is equal to weight by molecular weight. So moles into molecular weight is nothing but this is weight of this helium gas. This is also moles into molecular weight of argon. This is for argon. This 25 into 83.8 is for krypton. This is 25 into 131.3 for weight of xenon. Then after solution, this will obtain 6477.5 kg. So these are from this one we can estimate what are the mass fractions. Mass fractions are nothing but individual weight divided by total weight. Okay, here you can write this as y. Since these are the mole fractions for the gas phase, we can write this as a y. Accidentally x. Coefficient, we are using x for liquids, y for gases. So we can write here as y helium. So individual mass divided by total mass. So individual mass of this helium gas is this one, 25 into 4, whereas total mass is this one for the mixture. So this divided by this is this one. So individual mass of this argon is this one, 25 into 40. Then total mass of this mixture is this one. So similar fashion we can calculate the mass fractions. Okay, then average molecular weight. Average molecular weight is nothing but the total mass. Total mass divided by whatever the basis we have we have considered 100 kilomole overall mixture. So this one will come this one. So total pressure already they have given, T is equal to 200 Kelvin, and PT total pressure is 100 kilopascal they are given, and R value we have to just calculate the R value. Otherwise we have to remember this 8.314 kilopascal meter per variables are there. 100 kilopascal is there, 8.314 R value is there, 200 Kelvin is there. After estimating, we will obtain this kilomole per meter cube in terms. We can obtain this value. Then what is the density or the mass density they have asked? Mass density or the mass concentration. Okay, when mass fraction, when we have a molar concentration, this is molar concentration. We already have a molar concentration. So molar concentration is kilomole per meter cube. We want kg per meter cube, this one. So we have to just multiply it with molecular weight. So this is C is for overall gas composition. So overall C total concentration. So this is total mass concentration. So average molecular weight we have to use. This is average molecular weight. This quantity multiplied by this quantity will give us this mass density or a mass concentration. Okay, these two problems you have to practice for the next class. Okay, in the next class I will ask these two problems once again, just without practice. Whatever the explanation I have given to you, it will be drained, it will be waste without practice. There are 21 problems, you have to practice a lot for these problems. Okay, do you have any doubts? Okay, Pavani. Yeah, any doubts?
No, sir.
No? Yes.
No doubts, sir.
Okay. Then Isaac.
Sir,
Isaac. Yeah, do you have any doubts?
no, sir. This class I missed half an hour of first class, sir.
Okay, you can.
Laptop problems. So I will check on that offline video, sir.
Yeah, yeah, no problem. You can watch. Attendance is no problem. Okay, then Ravi, you just practice those problems.
Yes, sir.
Yeah, if you have
Sir,
any
your
doubts.
yes,
Hmm.
sir. I have seen the that nine sums
Okay.
in that question paper.
Yeah, yeah, yeah. Many problems are
Understand?
there in that one.
No, sir. You
So,
said that is ninth problem that we have done on the day.
yeah, yeah, yeah.
So I checked it. It is hard to understand this writing, sir.
Writing, that's what I am saying. My writing
Yes,
is
sir.
very hard to understand.
Yes, sir.
Yes, sir.
Some seems to be easy, sir, but we have to understand what the statements are given. That is
Mm. Yes,
difficult.
sir. That is difficult, sir. Uh,
Yes, yes. That's why I
Understanding
just
question.
underline. That's why I just underline what is the required data we have to extract from this one. So I will
Yes, sir.
once again explain all these problems. I will try to
Yes, sir.
explain this. Okay, no problem for that one. So whatever
Once we
before that,
understand question, we can do the rest of the answer.
yeah, yeah. Before that, you have to just read a problem. Okay, one or two
Yes.
times when you read those problems, then I will explain. Then you immediately catch. Now, see with the first problem when I explain, many of members I will clearly bet that many of members that doesn't listen also, and they will clearly don't understand also. When you
Yes.
try hardly that you read one or two times, then you just whatever the underlined portion. I also solved the same problem using. I doesn't refer to any type of textbook to solve these problems.
Yes, sir.
From the using formulas only, I just understood this problem by underlining what they have given, what are the data I have to extract. Okay, one or two times just read that problem. Then I will
Yes,
try
sir.
to explain this clearly. In the each class, I will try to explain one or two problems because I have to cover next unit also.
Yes, sir.
I will plan in such a way that I will start unit 2 in the next class. Then what I have to do 45 minutes I will go through the unit 2. Then only
Yes.
15 minutes I will do a problem. One or two
Yes, sir.
problems,
Yes, sir.
whatever.
Okay, sir.
Okay,
Okay, sir.
that's the case. Yeah. Okay. Hope you enjoyed the class. Okay. If you
Yes,
have
sir.
any doubt, just contact me. Okay. If
Yes,
you are
sir.
not asking any doubts, that's why I'm
Yes.
afraid. Am I teaching you correctly or not? What is your feedback? You can share your feedback. Okay, you
Sir,
are not.
you are deriving those formulas, no, sir?
Yes, yeah.
Just after deriving the equations and the final formula, explain a question on that formula, sir, on that particular formula.
I don't catch your words.
You did four derivations, no, sir, in the first unit.
Yes, 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 yes.
We got the final equation which is required, no, sir.
Yeah, yeah, yeah. Mm-hmm.
Derivations. Just
That's
after the completion of the derivation, give us the problems. Application of that problem. Application of that equation in
Remember
the
we
problem.
will apply.
Okay,
then only
okay,
we'll
yeah,
apply,
yeah,
sir.
yeah, yeah, I
So
understood.
time will be.
What happens, these are very big derivations, so you already seen my live board is just troubling me
Yes,
every
sir.
time. Because of
Yes, sir.
that, instead of explaining in a single class, I have taken from A through non-diffusing B liquid case 3 classes I have taken.
Yes, sir.
That's what I am shocked when I am uploading that videos in the Microsoft Streams. I just shocked, how can I take 3 classes for this simple derivation? Maybe
Yes,
because
sir.
of live board only, the problem will happen. Okay, no problem, I will just explain that one. These
No,
for the
sir.
convenience, for
While
your
you are
convenience.
explaining derivation, just
Yeah, yeah.
after when we got the required equation,
Yes, yes.
give us a problem on that equation to
Okay,
apply
okay.
it in
From
that
now
problem.
onwards, we will try for the next unit.
Yes, sir.
Please excuse me for this time. Okay, for the
Yes,
first
sir.
unit,
For
I
next
can't
unit
say.
onwards, we can do that, sir.
Yeah, yeah, yeah. For your convenience only, the required formulas I have just given in PPT.
Yes,
You
sir.
see that these are the formulas which are used. Okay, these you
Yes,
can
sir.
note down. Yeah. Okay, from the next unit onwards, I will try to do that one. Huh?
Yes, sir.
Please excuse me this time. Sorry
Yes,
for
sir.
the inconvenience.
Okay, sir.
Okay, thank you. Bye.
Thank you, sir.
Thank you, sir.
Bye.